Hello, everyone, and thank you for joining us for today's office hours. I'm Haley Matisow, and I'm here with co-founder Ingo Mierswa, this week's product expert and special guest. Throughout the next 20 minutes or so, Ingo will be taking you through a live demo on automatic model selection, as well as taking any questions that you may have submitted through Twitter with the hashtag RapidMinerOH. After the live demo, we'll be addressing your questions, so again, feel free to submit them through the Twitter feed. You'll be able to see the questions at the bottom of the RapidMiner office hours page. Now I'll pass it over to Ingo.
Hey, thanks, Haley. Hi, everybody. So today in the office hour, it will be about automatic model selection, which is, of course, an important topic, picking the right model for your data set and your use case and problem you would like to solve. It's also a pretty difficult problem. In fact, it's so difficult that some people have been creating a theorem which is called the very famous no free lunch theorem around this problem. So let's first talk about the problem. The problem is you would like to find the best and optimal machine learning model for your data. But unfortunately, it has been proven by, I think, two gentlemen named Volpot and McReady that there is nothing like a perfect model for all data sets. So you really need, at the end of the day, to figure out what model is working better for your particular problem versus others. So I will show you how to actually measure this, how well the model performs, and then also how to automate this whole process to get to the best model quickly. All right, let me share RapidMiner with you. Let's see. Here we go. Start screen share. All right. I hope you can see my screen now. So as I said, so the whole idea is let's try different algorithms. And really, as I said before, you need to try different algorithms to figure out what works best. So that's also the reason why it's good to have many algorithms. So here in RapidMiner, we have a total of 250. We're not trying all of them, and that typically doesn't make a lot of sense because not all are feasible in terms of runtime and other reasons. But let's at least try a few. All right, so this is the RapidMiner, the blank screen here. Probably most of you know this already. Let's start with some data set. Actually, I've prepared some data here as well. Let's start with this Sonar data set. So this is a very famous data. A lot of numerical columns. Let me quickly show it to you. In total, steered columns here. We see them here. All are numbers, and then there is this one class or label attribute here, rock versus mine, we would like to predict. All the columns actually represent the different frequency bands for sonar equipment, and based on those frequency bands, you would like to predict if something is a mine or a rock. So if you look at this data set here in this parallel chart, you see all the blue lines are rocks, all the red lines are mines, and you would like to figure out and predict, okay, if you get a certain sonar signal, what case is that? Anyways, that's not important for our task today, but it's certainly interesting to see, well, that probably there are some areas where rocks differ from mines, so it should be maybe possible to use a machine learning method to find those differences and thresholds, but let's see. So one way to measure this are cross-validation, and I know this was a topic for an earlier office hour, actually to find or work with cross-validation in a little bit more advanced way, just as a term. So the cross-validation is dividing the data into 10 parts. In this case, it's 10 parts. It's a 10-fold cross-validation, and trains the model out on 9 parts of the data and applies the model on the 10th part. And then it iterates through all the 10 parts for the model application and builds the average. So cross-validation is a very typical approach for evaluating how well a model works. And you can see that I can dive into this cross-validation here by just making a double click. This indicated by the small icon here. All right, so now I have the two sub-processes, one for training, one for testing. And let's start with the process, let's say, with the decision tree, which is a very frequent model. So let's drag it in, connect everything. And then for the testing, I'm applying the model. Drag it in again. And then I also calculate the performance. All right, let's drag it in as well. And some connections. Okay, so that's how you set up the cross-validation. Again, on 90% of the data, you train the model, then you apply the model on the other 10%. you get the average, and you can also deliver the model which is created on the complete data set. Okay, let's run this. And as we can see now, so this is the model, but that's not too important right now. As you can see that we can predict actually mines and rocks quite well here. But it's only an accuracy of 62%. So model selection, again, is about finding a model which is as good as possible. And 62% of this data set is not really great. So maybe we can try different models. So what you can do now is you can actually go inside of the cross-validation and replace the decision tree with other modeling techniques, let's say knife base. So now I'm adding a knife base here. And let's add this one, connect it, let's run the process again. And we can see in this case we are at 66.9%. That is a little bit better than the decision tree with 62%. So we're getting there, And let's maybe try something else. Let's say with an SVM. Let's drag in the support vector machine. Again, deliver the model here. Oh, wait a second. Actually, before I show the results, let's make one quick change, because many people believe that the SVMs are super good because they can also be trained for nonlinear data sets. So I changed this actually to this RBF kernel, or Radial Kernel as it's called here. And let's try this one instead of a linear one. Then the first thing I see is actually that the performance is not really great. So it's 53% only, and that's really just a result because it didn't learn anything. It just predicts the majority class, which happens to be mine, for all the cases. So that is not really good. So, which brings me to another thing, like you could now think SVMs are bad for this data set, let's not use them, at least the nonlinear SVM. But in fact, if you focus on one of the kernel parameters, gamma, which is a very important parameter here, and change this from 1 to, let's say, 0.1, and I run this again, then you actually can see that the prediction is 78% now. So that is much better than before, which was basically just guessing or predicting the default model or default prediction. But now we're at 78%, which is much better than the decision tree with 62 and the naive base with 66.9. So we found a pretty good model now on the Sonar data set, which is good. But that's, of course, not automated model design. So we saw now that it's really important to actually try the different models, the different model types, but also model parameters can deliver completely different results. So let's try this. But how can we do this really in an effective way? How can we accelerate the search? And in RapidMiner, but also in general, there are really like 3 different ways how you can do that. So the first way is to use helper methods, like, for example, a so-called ROC or receiver operator characteristics comparison. So you're calculating a visual representation of the performance of the model, and then you can, with one quick view, you can actually determine which is the best model. All right, let's start with this approach first. So let's just start from scratch with the new, actually even with the data, which is about predicting if somebody survived the Titanic accidents or not. So if I look at this data now, then I can see, well, this all the different information I have. Here's the important one, survive. That's the one we want to predict, which is defined by the role of the attribute, and there's an operator for doing so. So the set role operator, I can now just pick the survived column and say this should be the label. That's the one we want to predict. All right, good. So and now this operator I was referring to is called compare ROCs. So I just drag it in, and I deliver the this RC object here. And here again, I can dive in. And what we can do now is we see here we're getting the training data, and we have to deliver a model. So let's just add a couple of models here. Let's go with a decision tree. Let's also add, let's say, knife base. And last but not least, k nearest neighbors. And the default value for that one is 1. Let's maybe go with 5 nearest neighbors. This data set has about 1,300 different rows. Okay, so now all you need to do is you basically connect as many models as you want inside of this process. And then this operator here calculates which one is working best according to the so-called RC curve. So let me run this process and you see in a second what I mean. This is the result. If the model would be just random guessing, you would get for this model a straight line, which is the diagonal on the screen here. So all three models are better than guessing, at least that. The KNN model is not really that great. It's better if you go further to the top left with this curve. But the blue one and the green one, which is the decision tree and the naive Bayes, they're actually both doing quite well. In certain areas here, the blue one on the decision tree is better. In other areas, there might be the naive Bayes. So in fact, if I see a picture like that, without going into the details of the different confidence thresholds and everything else, it's probably worth trying both models, really. But I wouldn't spend a lot of time working on the KNN, maybe with a more optimal parameter for K. But it gives you a very quick insight, and it's doing all the stuff for you. So it's doing the cross-validation for you and the comparison, the visualization. So you will actually, with one single operator, and the only thing you need to define is the different model types, and then this one single operator will deliver this insight already. So that is one way how you can kind of optimize or automate this process and accelerate this model selection process. The second approach is what we call automated model or automatic model selection, which is the main topic of the office hour today. Actually, let me just load this process here. So this is the process. We retrieve another data set. In this case, it's a churn prevention data. So it's about predicting who's going to churn versus who's staying as a loyal customer. And then we will see this is a new operator here, optimize parameters. What this one is doing, actually, maybe I will get rid of this for a second and show you first the inner operator here. Let me do that. I think that's more helpful. All right. Okay, let's have a look first what's happening here. So I added this operator first here. Forget about the optimized parameters for now. I added this operator here, which we call select subprocess. And if I go inside, you can see that I have three different subprocesses in this operator. And I can add another one and delete it again if I want, but let's just go with those three. And every single of those subprocesses is just calculating a cross-validation, one cross-validation for a decision tree. And then let's go up again, one cross-validation for a naive Bayes. The models I just used before on the other data set, and K nearest neighbors again, with a value of 5 again. Okay, good. So if I run this process now, right now, I would get just the result for the first model, which was the decision tree. So that is defined here by this parameter select which. That means this operator here performs the inner subprocess number 1. All right, let's getting a decision tree. Not a very exciting though one though, and I get some performance which is 69%. If I now change this parameter to 2, for example, I get the naive Bayes model, which is this one here, so we're getting all the distributions here. I get the naive Bayes model, and this is actually with about 76% much better. The K nearest neighbors, and then again, I'm getting a performance which is less good. So the naive Bayes is apparently the best one. So that's simpler than what we saw before, because now the only thing I need to do is changing this value. But now the big question is, can I automate this? And the answer is yes. I just add another operator, this one here, optimize parameters in a grid. And that was the one I actually removed before. So let's add this one here. Let's go inside, and all I'm doing is I'm adding this select subparameter to deliver the best, and then I can deliver other results in addition to this. It can be defined in this way that I actually can say like, well, I take the try model select subprocess operator here. I would like to try to just select this one, and I would like to try out all 3 parameters from 1 to 3. In 10 steps doesn't really matter because it's just numbers, so it's automatically calculating, well, I will try the values 1, 2, 3. And of course, if you would like to try 50 different models, you can do that as well and automate this whole process for that one as well. But let's stay with 3 for now. So now this process is running, and what we are getting is that indeed the naive Bayes model is the best, with about 75, 76% accuracy. By the way, the reason why this accuracy is not exactly the same as before is because every single time here this cross-validation is executed, it takes different random numbers. And before, every one of those have only been executed once, but now we're actually executing this one here, or all 3 in a row. If you want to have like an absolute predictable behavior here, you can do this by specifying this parameter use local random seeds. If you do this, then you would actually get the same result, no matter if you use this as part of a bigger process or just this one step alone. All right, so that is really the whole, you automate the whole model. So we have the compare rocks or RSC curves. We have this automatic model selection, again, the main topic for today. You can do a lot of interesting things here. And the third one would be using something which is called Metalearning. Metalearning is a very interesting, but also completely different approach to this problem. And it's based on the idea that you can predict how well certain classifiers will be able to create correct predictions for a data set. So basically, we create a machine learning on top of other machine learning models. That's why we call it meta-learning. And so how are you doing this? Well, you need to somehow make the different data sets comparable. And you're doing this by calculating so-called landmarking features. So they describe the different data sets. Simple stuff like size of the data set, how many columns, how many rows, what are the types of the columns, what are some basic statistics around the columns. And all those landmarking features are used as an input for those different data sets. And together with the information, what is the machine learning model which is used and how well was the accuracy then? And if you do this, you can train another model which is predicting for a certain algorithm, for certain data sets with those properties, how well this algorithm will work. That is actually available in RapidMiner as well as an extension. So if you're not familiar with this, there's this marketplace here. You can go there and install additional extensions. I already did this, and the extension I'm talking about is the ML Wizard extension. It's an extension which is not created by RapidMiner, so by the company itself. It's a third-party extension. I really love the idea, but there's a couple of caveats, though, I have to admit. If the data sets are really, really large, then this extension does no longer work very well just because it's too much computation going on. But I will tell you, at least for smaller data sets, for binary or general classification problems, it can be extremely useful. All right, you will find it then under Settings and Automatic System Construction. And that's what happens. You only have 3 steps. The first step is you pick a data set. So let's go with whatever, the Sona data set. So you pick the data set, now it's analyzing the data, it creates the landmarking features, and it creates also the predictions how well the different models work. So it tells you right away that probably the best algorithm is rule induction, which is questionable at least, but okay. Then in neural network, then in SVM, decision tree, KNN, naive Bayes. So my personal favorite is not rule induction because I really think there are more powerful methods out there, so I wouldn't like to try that. But I'm a big fan of SVM, so let's evaluate this one here. We already know the decision tree, so let's skip that one, but KNN and naive Bayes, let's add them as well. All right, so you can select now what you want to evaluate, but the important thing is it already predicts the accuracy, and this prediction typically is wrong, but what is important, that very often the ranking of those different learning schemes is correct indeed. So you can actually say now, like, well, it's more likely that an SVM is better than a KNN, which again is more likely to be better than a naive Bayes. All right, so by checking those checkboxes now, we're actually calculating the actual accuracy for the different techniques. So that might take a while, although not that long. All right, so now you see we are done with naive Bayes and KNN already. So naive Bayes, it's 67%, not quite the 71 which was predicted, but at least it's less than the KNN, which was predicted better. And that again is less than the 91, which is amazing actually for the SVM, which was out of those 3 I selected the one with the highest rank. So then if you say like, well, I would like to use it, all you can do is click on load here and then on finish. And then RapidMiner creates the process for you, and not just the pre-processing and everything, but also it shows you the parameters which automatically have been optimized for this SVM. So that can be extremely powerful, especially on smaller data sets. So definitely worth to try out. So last thing really that I would like to cover then is, well, we talked about parameters as well and how important they are. We saw in the beginning how large the influence can be on the support vector machine, for example, the gamma parameter for the RBF kernel. Here again, we see that they are very well specific values. So how can you optimize parameters in general? Well, I have prepared another process for that. And you know this operator already, actually. So there are a couple of different ones. You can use evolutionary algorithms for parameter optimization. And this one is using this grid approach. So same operator you saw before for the selection of the different sub-processes or models. But now you can actually also go inside here and you can see like, okay, I would, for example, optimize this is polynomial kernel, the degree and C, which are both very important parameters for a polynomial SVM. Let's optimize those two values of this SVM here. And at the same time, also let's log some information, the current value of C, the current value of degree, and the absolute error. In this case, it's a regression problem. So if you do that now, you can actually now optimize for those two parameters. So C between 50 and 250, degree between 1 and 5. All right, let's execute this process, which is relatively fast. So you see it's, maybe you saw it, it was still running when I moved over here. So this is now all the different values for C and the degrees and the performance. And you can easily plot this as well. So you get an idea what is the best degree and what's the best value for C. So for example, here on the axis, y-axis, you have the different degrees. So degree of 3 actually delivers the smallest absolute error, and for C, 300 is over here to the left, so the larger the C, the better it is for this particular case. So you can actually find out what's the best parameter settings as well. And of course, you can then also combine both approaches. That's really the last thing now. You use one optimized parameters here for selecting the sub-process. You've seen this before. And then you have a second one here, for example, which is optimizing for an optimal K, for K and N. And if we run this process, we will see that actually still the naive Bayes is a little bit better. So we have this distribution model here still with the 75%, then even an optimized K and N. But you can combine those two things. And I think that's really one of the things which excites me until today, and since so many years now about RapidMiner, that you really can combine so many different aspects around optimizing out the right model and building really very complex processes, optimizing and all those things at the same time. And that's really what truly automatic model selection and automatic machine learning means to me. So yeah, that's how those processes are built. I hope you found this helpful, and let's give it back to Haley.
Great, Ingo. So you've automated the search for the best model and the best modeling parameters, but what about the input features? Can we automate the search for an optimal feature set, as well as combine this with model selection and parameter optimization?
Oh yeah, absolutely. So same idea I tried to bring across in the last example, where we combined the parameter optimization and the model selection. You can also now, there are operators for doing an automatic feature selection and even an automatic feature generation. So you build new features or new attributes based on the existing ones. So they are, for example, genetic programming operators inside of RapidMiner. So you can combine those again with the other optimization functions and build really like a very large process which optimizes everything at the same time. But showing this would be probably a topic for another office hour. That would be probably too much for today. But yeah, the answer is yes, you can combine that one as well. So maybe you should also check if maybe somebody also posted.
Ingo, so it doesn't look like we have any additional questions at this time. As a reminder, this is recorded. This is being recorded, and it will be available on our YouTube channel. So thanks again, everyone, for joining us, and feel free to join us next week as well. Have a great day, everyone.
Thanks. Bye.